So what about the weak acids? With the weak acid, in order to find the hydronium ion concentration, we need to solve an equilibrium problem. And that's because the weak acid only ionizes partially. So the initial concentration we're going to assume is approximately 0. That's because the concentration of hydronium from the autoionization of water is very small. It's 10 to the minus 7 molar. And so most of the time that's not going to be significant. So we'll say we're starting with approximately 0. We're starting with 0 of that anion. And this is our initial concentration of our weak acid. So then we use X to indicate how things are changing. This is going to decrease by X, this is going to increase, and this is going to increase. And then we add the rows, and so we have 0.1 minus X is the equilibrium concentration for the acid. X is the hydronium ion concentration, and X is also that counter ion concentration. And then you use your equilibrium constant, your Ka, and you solve it. Now, a lot of times, we can use the X is small approximation so that we don't actually need to use a solver. So any questions about the big idea here? Let's do an example. Find the hydronium ion concentration of a 0.250 molar hydrofluoric acid solution. Now, it's great if you know the formulas of the acids. If you don't, the thing you need to know is it a monoprotic, a diprotic, or a triprotic acid? And usually that gets kind of said in the problem somewhere. So here I'm going to write the chemical equation. So the hydrogen fluoride is going to ionize. And you can do this different ways. I'm just going to do it the simple way and use H plus and not have the water molecules in there. But we understand that this H plus is actually hydronium ion. So an ice table, we need an initial concentration. So the initial concentration of the weak acid is 0.250 molar. We're going to say the initial concentration of hydronium is approximately 0 because it's so small, and the concentration of A is 0. So those are our initial values. Then we're going to look at how do these things change. So the HF is going to dissociate or ionize and form these ions, and so this is going to decrease by X. This is going to increase by X, and that's going to increase by X. And there aren't any 2s or 3s or anything because these coefficients are all 1. So when one molecule of HF ionizes, we get 1 ion of H plus and 1 ion of A minus. And then at equilibrium, the acid will be 0.250 minus X, and each of these will be X. Now on this one I'm going to write it out in a little more detail, and then I'll be doing it more abbreviated for the rest of them. So the equilibrium constant expression would be the concentration of the products, that's an A, divided by the concentration of the reactant. Here we have one reactant. Oh. So, anybody wondering how an F turns into an A? Nobody? Yeah, but if I'm going to use that, then I should call it HA. Sorry. So this is fluoride ion. There we go. Having connection issues. So we know what the Ka is 3.5 times 10 to the minus 4. And so that will equal the equilibrium hydrogen ion concentration, which we're saying is X. So that's X times the fluoride ion concentration, which is X. So let's just call that X squared, divided by the HF concentration at equilibrium, which is 0.250 minus X. So you can plug that into a solver. A lot of these, though, we can use the X is small approximation. And so what we're saying is, because this is a weak acid, X is going to be small, and compared to the 0.25 that we're subtracting it from, it's not going to matter. So for X is small, we're just going to leave off this part right here, the subtracting X. That's going to give us X squared equals 3.5 times 10 to the minus 4 times 0.250. And then we don't want X squared, we want X. So to get rid of that, I'm going to take the square root, and then I can get rid of that. So this is something that's relatively easy to do. It doesn't require a solver. And so I come up with, X equals 0.0094. So I'm using the X is small approximation. I'm going to assume that X is so small that when I subtract it from the 0.25, it doesn't make any difference. So now I've found out what X is. Do you remember how we test the X is small? This X must be less than 5% of anything we're subtracting it from. So to test that, we take this 0.0094 and divide it by 0.250, because that's what we're subtracting it from. Multiply by 100, and that should be less than 5%. And it is, it's 3.7%. So if that's less than 5, we're okay. If it was greater than 5, then we need to use the solver and do the whole thing. So then we kind of have, we were doing all this stuff, and then we were, well, what were we actually trying to do? We're trying to find the hydronium ion concentration. Well, the hydronium ion concentration happens to be equal to that X that we found. So hydronium ion concentration is 0.0094 molar, or 9.4 times 10 to the minus 3. Any questions? Yeah.
Why is the hydronium ion equal to the X? How's that?
Because of our equilibrium line here, our row. We're saying at equilibrium, the hydrogen ion concentration is equal to X, and the fluoride ion concentration is equal to X. If we wanted the HF concentration, we'd take 0.25 minus this, and we'd find out that, yeah, that's essentially 0.25. Anybody else have any questions?
Is that the percent ionization?
No, that's not the percent ionization. Well, it kind of ends up being that, but that's not what we were calculating. Because we haven't talked about that yet. Let's find the pH of a 0.0150 molar acetic acid solution. So we've got acetic acid, and that's going to ionize and form hydrogen ions and acetate ions. And so we're going to make an ice table. The initial concentration, what's the initial concentration of acetic acid? Just what it says, 0.0150. So that's initial. Initial concentration of hydrogen ions? We're going to say it's 0 because, it's 10 to the minus 7. It's really small. Initial concentration of acetate? 0. So equilibrium happens. How do these things change? Well, it must go to the right because there's nothing over there. So we're going to lose acetic acid, and we're just going to say, well, we'll lose X of that. And then we're going to gain X for the hydrogen ion and for the acetate ion. Which tells us that at equilibrium, we're going to have this concentration being 0.0150 minus X. The concentration of hydrogen is X, and the concentration of acetate is X. Everybody with me? We're given Ka, the acid dissociation constant. That's the equilibrium constant for this equation. So Ka equals this 1.8 times 10 to the minus 5. And that equals the concentration of each product. There's no coefficient, so we don't have to worry about exponents, divided by the concentration of the reactant. So X times X is X squared, and then that's divided by 0.0150 minus X. I don't want to be too brief in what I'm doing on the screen and lose you, but I also don't want to bore you to tears by doing the same thing over and over and over again. So if I'm going too fast or too slow, please tell me. Let's try the X is small again. So if X is small, then subtracting it from 0.0150 shouldn't matter. X is small says that X squared equals the, Ka times the initial concentration. And then to get X instead of the square root, instead of X squared, I take the square root. So by taking the square root, then these guys is just X. So it's really the same calculation with just different numbers from the previous slide. And X equals 4.7 times 10 to the minus 4. We need to check that and make sure that our approximation is okay. So we're going to take our X and divide it by 0.015. Multiply by 100. I get 3%, 3.2%. Yes? Oh, okay. Let's see what I did. Oh, I did 1.5 times 10 to the minus 5. That would be a problem. Let's fix that. Thank you. Yeah, how about 5.2 times 10 to the minus 4? (5.2 times 10 to the minus 4). Okay, so let's check that divided by 0.015 times 100. So 3.5%. So X's small approximation is okay. So X is equal to the hydrogen ion concentration. right? And we're asked to find the pH. So pH is the negative log of that. .28. Any questions? Yeah.
You wanted to define the OH, the pOH of this one. You just do the 14 minus the.
Yes. If you wanted to find pOH instead of pH, just take 14 and subtract this number.
You could do that with the Ka and Kb.
We will see how the Ka and Kb are related. But yeah, they are related through that as well. Any other questions? So finding the pH of a weak acid solution when X is small doesn't work. So the title is telling us it's not going to work this time. We're going to try it anyway and see that it doesn't work. Okay, so here we have nitrous acid. So we've got HNO2, and that's going to ionize and form hydrogen ions and nitrite ions. And we have an initial concentration for this nitrous acid of 0.010. That's our initial. And we're going to assume 0 hydrogen ions, and we know there's 0 nitrate. Then for our change, we're doing minus X for this and plus X over here. It's a bit repetitive, but, you know. So here we've got 0.010 minus X. And here we've got X, and here we've got X. And so those are the equilibrium concentrations in terms of X. And so we can plug them into the expression. Ka is given 4.6 times 10 to the minus 4. That has to equal the products divided by the reactant. If we say X is small, then we're going to end up with that Ka value times the initial concentration and the square root of that. Let's see if I can put the numbers in correctly this time. Uh, 2.1 times 10 to the minus third. 3. 2.1 times 10 to the minus third. So the check is we take this number, divide by what we're subtracting it from, multiply by 100, 21%. That's much higher than 5%. So this is going to be large enough. It's going to be around this number, but it's not going to be exactly that number. This is large enough that when we subtract it from 0.01, it does make a difference. So I gave you the analogy a couple days ago about the truck full of oranges, right? And taking one orange off just is not significant in terms of the mass of the oranges in the truck. But if you have a box of oranges, you've got like 6 oranges in a box, and now you take one orange out, does it matter? Yeah, it matters, because what you're removing relative to the overall thing becomes significant now. 21% is significant. Less than 5% isn't. So we can't do X is small. So scratch this. Can't do that. What do we do? Well, use your solver. Okay? So I've got the TI-30X, 36X Pro, and I just type this in as it's shown there. 4.6 times 10 to the minus 4 on one side, X squared divided by the quantity, 0.01 minus X. Close the parentheses, tell it to start at 0, and solve. So using the solver, I'm getting x equals 1.9 times 10 to the minus 3. This is in the same ballpark as 2.1 times 10 to the minus 3, but it's not the same. So this is our x. We're trying to find the pH. Hydrogen ion concentration at equilibrium is equal to x. So here's our hydrogen ion concentration, and so we need the negative log of that to get the pH. .72. Any questions? Go ahead and use the x as small approximation. But when you do that, you have to check, because it's not always going to work. We can find the equilibrium constant for weak acid by measuring the pH of the solution of a known concentration. So here we have 0.175 molar weak acid solution. The pH is 3.25. Now we're asked to find the equilibrium constant, the acid dissociation constant. Well, we're going to do an ice table again. We don't know what this acid is, so I'm going to call it HA. So this ionizes and forms H+, and there's the A-. The initial is going to be the same as what we've been doing. Here's our concentration of the weak acid. So we're going to start with that, and we're going to assume that there's not a significant contribution from water itself, and that we have none of the conjugate base. The change, minus x plus x plus x. So at equilibrium, what do we know? Yeah, so at equilibrium, our HA concentration is going to be 0.175 minus x. What we were doing before is we were taking the Ka and we were plugging all these x's in on the other side, but now we don't know the Ka. We're trying to find the Ka. Do we know anything about any of these equilibrium concentrations? We can find it because we're given the pH. The pH is going to tell us what the equilibrium concentration of the hydrogen ion is. So the hydrogen ion concentration is going to equal 10 to the negative pH, which is 10 to the negative 3.25. Um, 5.6 times 10 to the minus 4. So that's the equilibrium concentration of the hydrogen ion, 5.6 times 10 to the minus 4. Does that tell us what x is? Yeah, because we started with 0 and now we've got this much. So now we know that this is equal to x. So 5.6 negative 5.6 times 10 minus 4. So here for HA, we've got 0.175 minus 5.6 times 10 to the minus 4. And so that gives us 0.174. Not very different, but a little bit. Ka, again, equals the hydrogen ion concentration times this conjugate base divided by the weak acid concentration. So we've got 5.6 times 10 to the minus 4. And that's the same for both of these. So I'm just going to write it as that squared. Divided by this 0.174. Getting 1.8 times 10 to the minus 6. I took a picture of the answers, so I'm checking my answers. There's lots of places where you can screw up in these. Any questions? Percent ionization. The percent ionization is a percentage, so it's the part over the whole times 100. It's the part that's ionized divided by the part that is not ionized, the whole thing. I'm sorry, not the part that is not ionized. It's the part that's ionized divided by the whole amount of acid. So we can use the hydronium ion concentration at equilibrium as an indication of what the ionization is, and we'll divide by the initial concentration of the acid times 100. So for weak acids, this percent ionization is going to be pretty small because they only ionize a little bit. So it's not going to be like 75%. It's going to be like 5%. Find the percent ionization of a 0.250 molar acetic acid solution at 25 degrees Celsius. There's the Ka. Is this the one we did? No, that was something else. Sometimes these refer back to each other, but not this time. Well, I'm tired of writing acetate, so I'm just going to call it HA. So initially we've got 0.250 molar, 0 of this, 0 of that. The change is minus X, and plus X. And at equilibrium, we've got 0.250 minus X, X, and X. Equilibrium constant, the Ka should equal X squared over 0.250 minus X. So if we do the X is small approximation, I'm getting 2.1 times 10 to the minus 3. So when we divide that by what we're subtracting it from, I come up with 0.8%. So that's cool. So percent ionization, we need this initial concentration of our weak acid, and we need the hydrogen ion or hydronium ion concentration. So when we find X, we are finding the hydronium ion concentration. So percent ionization is going to equal our hydrogen ion concentration at equilibrium divided by our weak acid concentration initially times 100. So we've got 2.1 times 10 to the minus 3 divided by 0.250. And that ends up being that percentage. So it's 0.85%.
So that would vary just when we're given initial concentrations for the...
Yeah, this will vary based on the initial concentration. It'll vary based on the equilibrium constant, the Ka, for that acid. That'll cause the percent ionization to be different. But when X is small, then this percentage ends up being the same as what we get when we check this to see if X is small is valid. It's kind of a fluky thing. Any questions? So what we see for weak acids is that if you increase the initial concentration of the weak acid, the concentration of the hydronium ion at equilibrium increases. Right? You put more acid in, you've got more hydronium ion. What doesn't always make sense is that the percent ionization actually decreases as you increase the concentration. So the actual amount of hydronium ion is increasing, but relative to the original amount of the acid, the percent ionization is decreasing. So the way your book looks at it is, say at equilibrium we had, come back. Let's say at equilibrium we had 1 mole of this, and 1 mole of that, and 1 mole of this. And we add water to that and dilute it, right? So we're decreasing the concentrations of all of these. But what's that going to do to the equilibrium? Is it going to go to the right or to the left? It's not going to be the same because we have more moles of stuff over here. It's going to go to the left. And so that's why the ionization constant, the percent ionization energy, I'm mixing all of them up. The percent ionization decreases. And you can do, the calculation, pick 2 concentrations and do the calculation, and you can kind of prove it to yourself that way. Okay, so what if we have mixtures of acids, more than one acid? This could be really complicated, but most of the time we can just ignore the weak acid and look at the strong acid, because it'll turn out that the contribution from the weak acid is so small it doesn't matter. So if we look at a mixture of 0.1 molar HCl and 0.1 molar HCHO2, this is formic acid, there are 3 sources of hydronium ions now. We've got the strong acid, we've got the weak acid, and we have the autoionization of water. So here's the strong acid. It's going to go completely to forming hydronium ion and chloride ion. Here's our weak acid. That's going to form some hydronium ion. And then here's the autoionization of water. So the strong means it goes all the way to the products. And here's our constant for the weak acid. And we see that the constant for water is so much smaller, we can just kind of tell that that's not going to be important at all. The other thing that goes on here, just besides the difference in the Ka values, is that this hydronium ion concentration actually suppresses the formation of hydronium ion from the weak acid. Because if this was at equilibrium and then you toss the HCl in there, you've added a whole bunch of hydronium ion. And what's that going to do to the equilibrium of the weak acid? It's going to push it towards the acid, away from the hydronium ion. So we can look at this example here. Initially, 0.1 molar of the formic acid, the weak acid. And here, we're saying 0.1 molar of the hydronium ion because that 0.1 molar HCl completely ionizes and forms 0.1 molar hydronium ion. So that's 0.1. And then our initial concentration of the formate is 0. So then we can do minus x plus x plus x. Now we've got at equilibrium 0.1 minus x, 0.1 plus x, and x. And we can combine those and solve for x. And we find that x is equal to 1.8 times 10 to the minus 4. This is small enough that when we add this to 0.1, it just doesn't make any difference at all. So the contribution from the weak acid is negligible. Doesn't matter. It's too small. The contribution from the autoionization of water is even smaller, so we don't even need to talk about it. Any questions? So that was a strong acid and a weak acid. What if we have two weak acids? Well, there's still the three sources from each acid and from water itself. There are situations in which we can ignore the weaker of the two acids and the water. So if the Kas of the weak acids are different by more than a factor of several hundred, so if their exponents differ by several digits and the concentrations of those acids are similar, or we have the stronger acid present in a higher concentration, then the weaker acid isn't going to matter at all. So let's look at this one. We've got a mixture of HF and HClO, so hypochlorous acid and hydrofluoric acid. And this slide is in the wrong place. This is finding the, or it's got the wrong title. Hang on a minute. Okay, so now I've got the correct slide, and I've got that toolbar at the bottom. I'm just going to ignore that. Okay, so we're trying to find the hypochlorite ion concentration in this mixture. So we've got 0.3 molar HF. Here's its Ka, 10 to the minus 4. And here's 0.1 molar hypochlorous acid. Its Ka is 10 to the minus 8. So those exponents differ by 4. So that's what, a factor of 10,000? So we can assume that this is not going to contribute significantly, and all we have to do is look at the HF. So we've got the HF. Initially 0.3 molar. We also have, this is the stronger acid because it has a higher Ka. We have more of the strong acid than the weak acid. If we had very little of the stronger acid and a lot of the weak acid, then we should look at both of them. So starting out 0 and 0, plus x and minus x. They're not actually all the same, although it's looking like that right now. So we're going to find out what x is here. Ka is 6.9 times 10 to the minus 4. And that's going to be the x squared over 0.30 minus x. And we're going to try that x is small approximation. And solving it with x is small, I get x is 0.014. That's not looking good, is it? Huh? Just barely. So we divide by 0.3 to check it, and I get 4.8%. It's less than 5, so we'll go with that. So X is 0.014 molar. So that's what the hydrogen ion concentration from the HF is. Right? So hydrogen ion concentration here is 0.014 molar. Is that answering the question we're asked? No. We're asked what the hypochlorite ion concentration is. So that's going to come from this other weak acid. So the initial concentration of the hypochlorous acid is 0.100 molar. Can we say that the initial concentration of hydrogen ion is 0? No, because we've got this other acid present. This acid by itself would give us a hydrogen ion concentration of 0.014 molar. So that's what our initial hydrogen ion concentration has to be. Well, we have to have initial concentrations before we can do X. So what I found was for the HF, the equilibrium concentration of the hydrogen ion would be 0.014, and that was X over here. So now we're going to look at the ionization of the HClO, and so there is a significant hydrogen ion concentration. And I calculated this from the HF, which is the stronger acid. The initial concentration of hypochlorite ion is 0. So then the change, this is where we're going to put X's in. So this is minus, well, wait a minute. Yeah, minus X. Because it can't go to the left, can it? Because there's no hypochlorite ion. So it's going to the right. So we're going to lose concentration here and gain at each of these. Plus X, plus X. I should have used a different color over here. So I'm going to find out what this X is using the Ka for that acid. 2.9 times 10 to the minus 8 is going to equal 0.014 plus X times X divided by 0.100 minus X. If we say that X is small, so the X is small approximation says that wherever we're adding or subtracting X, we just don't need that anymore because it's not going to be significant. So I'm going to just say, well, let's get rid of that. Well, then that's pretty easy to calculate. X is going to be 2.9 times 10 to the minus 8 times the denominator of 0.1 divided by the numerator of 0.014. And so for X is small approximation, we find that X is 2.1 times 10 to the minus 7. Do we even need to check that against 0.014 or 0.1? That's much less than 5% of those numbers. So X's small approximation is valid. What is X telling us? X ends up being the hypochlorite ion concentration. So the concentration of the hypochlorite here is 2.1 times 10 to the minus 7 molar. The ionization of this acid does not significantly affect the hydronium ion concentration because it's so small. Questions?
So if we're checking that, because we
Mhm.
have the two different concentrations,
Mhm.
do we still just use the initial for the,
That's a good question. So when we're checking X is small, which one of these should I use? Do I have to do both of them? Use the smallest one. Because using the smallest one will give you the largest percentage. If that's 5 or greater, then you can't use it. Good question. Let's check my answers. So the book is saying 2.0 times 10 to the minus 7. That's pretty close. Any other questions?